Our last little bit here, we're going to start talking about reduction oxidation, and we're going to start with oxidation numbers. So we've made it through a lot of aqueous chemistry. Precipitation reactions, where we exchange ions. Acid-base reactions, we're exchanging a particular H+ ion. Both of these types of reactions, we can predict products using the double displacement pattern. Our third type of reaction we want to talk about are called reduction oxidation or oxidation reduction reactions. These involve the transfer of electrons. So you can see a lot of these reactions that we're talking about have kind of simple types of patterns. Exchange ions, exchange H+, or transfer electrons. These are simple kind of small changes, which are generally controllable, right? And so that allows us to make predictions, kind of understand what's going on. It is important to note oxidation reduction. For our purposes in this class, we cannot predict these. Don't worry, if you come back for Gen Chem 2, you'll learn how we can start to make predictions with respect to these reactions. But for our purposes, we're just going to work on analyzing these and understanding them, not necessarily completely dealing with them. Also important to note, these extend beyond the world of aqueous chemistry. Acid, base, and precipitation are fairly locked in. Solute water-based solutions. Oxidation reduction is more general, but we're going to talk about it still in this mindset and deal with it in the same way. So oxidation reduction is also called redox for short, a little bit of a nice shortening. They involve the transfer of electrons. Generally, these types of reactions involve a lot of energy. They're oftentimes used for practical purposes. Energy in terms of that we use it, either burning fuel is always redox, or batteries where it's a bit more controlled. You're still driving electrons. You're transferring electrons, in that case, through a circuit to power, say, a laptop. Also, things like bleach bleaches things via redox chemistry. Again, this is a really aggressive reaction, so we can use it for practical purposes. There are also cases like rusting where we don't want redox to occur. It's a real aggressive reaction that degrades the iron, and we spend a lot of time and money painting things to prevent that from happening. So the technical definition is that oxidation reduction reactions involve the transfer of electrons. This language, oxidation reduction, where we're breaking it up into two processes. These are happening at the same time, but what we end up thinking about is we're talking about transfer electrons. Well, we say oxidation, that's the process where some substance, say an atom, an ion, a molecule, loses electrons. And reduction is then the other substance that gains an electron. These always have to happen at the same time, right? What we're doing is we are transferring electrons. So say you have some atom, you have another atom, and that electron has to go from one to the other. So we would say that this thing has lost an electron. That would be oxidation. And this thing has gained an electron. That would be reduction. So the transfer of electrons, something always has to lose, something has to gain. That's where we get redox. So we do want to remember these rules, oxidation and reduction. There's going to be a lot of naming, and I understand it is confusing because reduction meaning gain is a little counterintuitive. We will learn where eventually that word comes from, but reduction is gain. I remember this using the mnemonic oil rig. Oxidation is loss. Reduction is gain. You grow up in Texas, that tends to be the one you learn. You may have also heard a different one like LEOGR, sorry. So LEOGR stands for loss of electrons in oxidation, gain electrons in reduction. If you're an animal fan, LEOGR, like the lion is growling, I think. I don't really use that one, but that is one that's commonly used if you want to. So the most important thing is that you remember oxidation and loss get paired together, reduction and gain get paired together. I know that seems a little silly with those words, and this is very easy to get tripped up on. So we do want to be careful when we're trying to put all that together. So when we're looking at reactions, we want to be able to see, is this an oxidation reduction reaction? And we know that means electrons are moving. So sometimes it's a bit easier to see because we have something like zinc in this case is not an ion, and then it becomes an ion. Copper ion becomes not an ion. That has to have involved the transfer of electrons. Or we have something like, say, two elements, say sodium and chlorine, combining to form an ionic compound. which means again that ions are moving, or electrons are moving between those atoms because you're generating ions. So those would be more clearly ionic oxidation reduction reactions. One of the things we can also see from this, you still have net ionic equations. This net ionic equation, you've removed any of the anions because they're just kind of floating around. You want to see where the electrons are moving. They allow you to focus on what atoms have changed and become ions and how they have changed. Other redox reactions are going to be more difficult to diagnose. We have C3H8 plus 5O2, our example reaction that we beat to death previously. That's oxidation. Hydrogen peroxide, H2O2, reacts to give you water and oxygen. That's also a redox reaction. And so these are much harder to diagnose. So we want to come up with a way that's going to be very clear, is this a redox reaction? There are some rules we can start to pick up. The first one is that combustion reactions are always redox reactions. It doesn't matter what you're doing. If you see combustion, which you can tell because oxygen is a reactant, that's a redox reaction. Similarly, I don't think it's on here, but anytime you have single replacement, this example up here is single replacement. The anions have been excluded, but single replacement reactions are always redox. You have something that's an element becoming a part of a compound, that's always going to be a redox reaction in order for that to happen. So combustion and single replacement, always redox. There's always electrons moving between atoms in those reactions. So we want to come up with a way to identify redox reactions. And what we're going to use are what are called oxidation numbers. So oxidation numbers they're kind of like a charge, but not really. They're going to be plus and minus. But what they describe is some sort of way to describe the distribution of electrons between the atoms in a compound. And so kind of basically the idea is like, what if this was all ionic? Now, we're not making ionic compounds. These are covalent compounds. And we're going to see what kind of where the electrons would go if they were ionic. Because we're just trying to get the distribution. Where are they located? So these are kind of like fake charges. They're not real charges, but they're mimicking what a charge would represent. And so if you have a change in oxidation numbers across a reaction, so going from an atom in the reactants to that same type of atom in the products, if your oxidation number changes, that is a sign that a redox reaction has occurred. And this is where the language actually comes from. Reduction reactions see a decrease in oxidation number. That's where that word comes from. Oxidation is an increase in oxidation number. So when you do oxidation, you make your oxidation number more. You get more oxidation. Your oxidation number goes up. Because these are charges, remember oxidation is loss of electrons. Electrons were negative. So when we lose negative charge, we end up getting a more positive charge, more positive oxidation number. Reduction is gain. You are gaining electrons, which are negative, so you get a reduction in the charge. So that's why, because many moons ago, someone had the grand idea of making electrons negative, and that's what causes all this confusion. It comes down to, we're mimicking charges. We're talking about charges, and reduction is gaining electrons, which decreases your charge because they're negative. So determining oxidation numbers is going to be an algorithm. Okay, so we're going to follow this process. We'll see it in action, but I just want to walk through it. Step one is you look for atoms that are elemental. Any sort of element, all atoms in that elemental sample have an oxidation number of 0. If you're talking about charge, if all the atoms are the same, they all have to be neutral because everything has to be neutral. If you have an ionic compound, your ions, your monatomic ions, their oxidation number is equal to the charge of the ion, right? You had your ionic compounds. The whole point, we're trying to make up like fake charges. We might as well use real ones when they're available to us. So if it's elemental or if it's ionic, we use that. When we get to a covalent compound, it's going to be a little more tricky. Certain atom types have preferences for what they end up with, similar to, our solubility rules. Certain ions have certain preferences. Well, certain atoms have certain stronger preferences for their oxidation number. The highest preference is fluorine, F. If you ever see F in an ionic and a covalent compound, it's going to go -1. Hydrogen is the next highest priority at +1. Oxygen is the next highest at -2. other halogens are the next highest at -1. So there's a lot more nonmetals than that, but that really gets us most of what we need. There are other rules, but with those 4, we can figure most things out. It's important to note that there is an order to this. So if fluorine's in the molecule, it'll take -1. Only if you still have flexibility does hydrogen take +1, and only if you still have flexibility does oxygen take -2. What's more important is the fact that the sum of all oxidation numbers for all atoms in a compound has to be equal to the total charge on that compound. So compounds are neutral. You need to all add up to be 0. This is similar to when we were looking at, say, figuring out Roman numerals, determining what that charge was going to be. If you have 3 oxygen atoms and they're all -2, that's going to give you -6. You need to balance that out. So those sorts of ideas. And again, we're going to look at an example to see this in action, this kind of algorithm process, but we can always use this process. So let's look at some examples. Determining oxidation number for each atom type. And again, for any particular molecule, each atom type is going to have an oxidation number. So F2, if I want to start with that, fluorine. This is one that does trip people up quite a bit because fluorine is a special case, but this is elemental. F2, this is fluorine. This molecule is just fluorine atoms. That's an elemental species. So fluorine in this case is 0. Only in molecules does fluorine get assigned that -1 charge. Next thing we have is CO2. So I want to look, carbon and oxygen each need them. It's not elemental, it's not ionic. So then I come down to my preferences. Well, oxygen is going to be given a -2. Oxygen always wants to be -2. So now the question becomes, what is carbon? And this is where I use the fact that the sum must be the total charge, where this is a neutral molecule, carbon dioxide. So the sum of all of the oxidation numbers must be 0. So if I think about that mathematically, basically what I'm saying is the carbon charge plus 2 times -2, that oxygen charge must be 0. So basically each oxygen atom is -2, and then I have 2 of those oxygen atoms. So then that'd be -4. Overall, my carbon must have a charge of +4. So the oxidation number of oxygen is -2 and carbon is +4. If I now look at sodium carbonate, this is an ionic species. So I can say right off the bat, sodium is a monoatomic ion, right? This is Na plus and CO3 2-. This sodium is then going to have an oxidation number of +1. Because the ion has a charge of +1, we'll just use that. So now I need to look at carbon and oxygen. That's a polyatomic ion, so I can't assign the charge from the overall ion to that. Instead, I need to use the rules I've used previously, that the oxygen is going to be -2 in this case. It has a higher preference than the carbon. So then when I'm looking to do the sum, now I'm looking for the sum of this carbonate ion. I have carbon and oxygen in there, and together the charge is -2. So when I look at the carbon and oxygens together, that sum needs to be -2. So this -2 matches this charge. This 3 oxygens comes from right here. And then I can see that I also then have a carbon from right there. And so -6 plus what equals -2? The carbon is +4 in this carbonate ion that we have right here. And actually, carbon's +4 in all carbonate ions, right? That didn't depend on the sodium, that just was from the carbonate. If we now look at P4O10, oxygen must be -2 here. Phosphorus doesn't have a preference. Total sum must be 0. So phosphorus times 4 plus 10 times the -2 has to be equal to 0, which means the phosphorus is +5, right? 4 times +5 is +20. 10 times -2 is -20. So you can have oxidation numbers, whatever you want them to be. They just need to be balanced out. Your charge sum up to that total charge. Participation 612, question 4. Determine the oxidation number for each atom type in the following compounds. A, H2O, B, H2O2, and C, KHCO3. This is the 4th question on participation 612, due Friday, June 12th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, determine the oxidation number for each atom type in the following compounds. A is water, B is hydrogen peroxide, and C is potassium bicarbonate. Okay, there was another participation question. Just one more video in this set. Looking for that any more participation questions in there. See you there.